Okay. And so, for example, right here, we have the element, simplest type of matter, because it's made up of only one type of atom. That's kind of true, but not really. There are simpler types of matter that have mass, but better definition would be an element is the simplest unit that still has all of its properties. Okay? So for example, gold, if you split gold over and over, once you get down to a single atom, a single element of it, then you're going to, any more splitting is going to cause that to no longer have its properties, right? Okay, again, the atom is going to be the smallest unit of matter that keeps its unique characteristics. Again, that definition is quite good. You'll notice it mirrors my definition. Okay. A compound is going to be a pure substance made of two or more elements that are chemically joined together. That's a good definition. That works nicely. Okay. All right. Now, a mixture is going to be a combination of two or more different substances. So it could be two different elements that are not actually bound together. They're just mixed together. Okay. It could be an element with a compound. For example, this right here is aerated. Does anybody know what aerated is? It means oxygen is dissolved in it. So the fishies could survive. Okay? And so that would actually be an example of a mixture, wouldn't it? You could have two different compounds mixed together, right? Anybody have sugar water of some sort? Yes, Dr. Pepper. Can you show it off for me? Thank you so much. Okay, that one's a mixture as well, isn't it? Okay, then we have homogeneous mixtures. This is one whose composition is the same throughout. So if you look at it and you can't tell the difference from one part to the next, that's going to be a homogeneous mixture. For example, your desk's lining on the outside is a homogeneous mixture. The board up there is actually a homogeneous mixture that's been written on, so there's other junk on it. And you actually have a bunch of examples of this around you. Do you need any more examples, or are we good to go? I think you're good. Okay. Does anybody know if you're looking at a homogeneous mixture right now, or perhaps through one? Yeah. The screens have homogeneous mixtures that you're looking through. That's the coatings. Also, you're looking through air, which is a homogeneous mixture. Okay? It's actually a nitrogen-based solution. Yeah. So heterogeneous mixtures, these are going to be ones whose composition is not uniform but varies throughout. This would be things like Chex Mix or your ceiling tiles are heterogeneous mixtures. Or your skin is a heterogeneous mixture. Everybody has like pores, right? And yeah, you can see little differences among your skin areas. So that's another heterogeneous mixture. This right here is the classification flow chart that I want you to have in your head to be able to use. And it's extremely important in sciences that we can break things down through definitions and that we have very clear definitions. Okay? Now, again, it's matter. That breaks down into pure substances and mixtures, right? If we have a pure substance, that breaks down into elements and compounds. Okay? Mixtures breaks down into homogeneous or heterogeneous mixtures. And again, these are some examples. This one right here is actually brass. Anybody know what this was originally referred to? Anybody play video games? Or RPGs or anything? Like Dungeons and Dragons? Ever heard of orichalcum? So orichalcum was actually brass. It's usually used now as like a fantasy thing that you collect, and it's like a quest. It's actually kind of funny, right? You go on this long quest, fight a dragon, you get orichalcum. You got brass. You got penny. Congratulations. All right, so periodic table of elements. You've probably all seen it. There is not one in this classroom, I don't think, which is a shame. One of the things I'm going to probably ask you to do is, if you could please go ahead and grab a periodic table and keep it in your book and bring it out in class sometimes. You're always going to have a periodic table I'll provide you one on exam. And usually I have one in the class and I can point things out in the classroom, right? I don't have room to have it on every slide. So I would ask if you could grab one of those and sort of keep it on your desk whenever we're doing lecture. Mm-hmm.
Are these PowerPoints on Canvas?
They are. Yep, they are indeed. So the periodic table of elements is going to be a listing of all the elements we have discovered so far. They're all the ones on Earth, plus all the ones we've discovered in any way whatsoever throughout the universe, known universe, and we have created. Okay? We sometimes spend long times not naming them because the organization that names them gets into fights and then doesn't speak for a decade. But it's true. They finally got back together like 5-6 years ago and started naming things again. Yeah, I think it was because one of the people died, if I remember correctly. So yeah, scientists are people too. We've had some legendary fights in science. My advisor actually absolutely hated IUPAC and used to cuss those people out. Very stubborn. Again, the periodic table is going to consist of small blocks. Each of the block is going to hold a different element, symbol, and atomic number, which is actually how these are arranged. They'll also list then the atomic mass within there. The letters are going to be chemical symbols. They're going to represent the name of each element. Each element will have a 2-letter designation. If you see a 3-letter designation, it means they haven't figured out the actual name for it yet. Okay? And that's a temporary naming. They have tried to mostly keep it what their names are, but that doesn't always work. And sometimes they have used mythological figures, actually quite often, or Greek and Latin. Okay? And so they are actually what they are, period, all the time. Just sometimes they're a bunch of different languages. So it doesn't always help. For many years, the symbols are going to be derived from the name of the element. Some symbols are derived from the Latins. For example, sodium, natrium, and A comes from natrium. So Latin for sodium. Gold is aurum, AU, and that's where the gold 2-letter symbol came from. It's actually the Latin name for it. Okay. Right here is actually an example of the periodic table. This is one of those things that the transfer from paper to digital actually really kind of hurts. Is they used to give you books, and in the book, the front cover, you would open it, and there was a pull-out periodic table. Okay? And so the periodic table would fold one page in size, and this is what it looks like when it's one page. Okay? And then you could then pull it, and it would fold open right here, extend out, and this actually inserts right here. Okay? So it has one of the elements in this row, and then it inserts between the two and lengthens out. Can everybody kind of mentally see that? Now, it does not work well if I put it on this proportion of slide, but if you go online, you can actually see the extended periodic table. It is actually something you might want to check out, okay? It makes a little more sense when you see it like that. Right. You will notice it has periods right here, 1, 2, 3, 4, 5, 6, 7, going down. It then has rows going across, and they're called groups. Everybody said okay? Fantastic. Okay, now I'm going to ask you to keep that in your head. You might want to pull that up on your computer, or if you have a printed version, take that printed version out. So the vertical column, again, is groups. These are going to be elements with similar chemical behaviors. We'll go into why that is a little bit later, but understand that everything about this periodic table is experimental. It was actually from the experimental what we saw. And so it's all due to very concrete concepts that just stack up. Okay? There's nothing random about a periodic table. And this thing is debated to the nth. You can't believe the amount of fights that have been had over this periodic table, and there's still some ongoing ones. For example, this one right here, whether these two are metals, metalloids, or non-metals, is fought over constantly, and typically changes every like 5 or 6 years because of a new test somebody figured out to try, and it came out with this result. To be honest, the metalloids, which we'll talk about a little bit later, are kind of like just understand that they're not really either, okay? And you're probably best off at this level. If you want to go into that, we can go a long time going into it. But also, hydrogen's location is a very fought over topic and is a whole thing, okay? Just accept it's weird too. All right. There's some stuff. All right. So each group has a number and letter designation. There's the A designation. These are the main group elements. Main group elements are this stuff right here, these, and these ones over here. Everybody see it okay? Okay. They're the more classical chemistry. They follow the classical chemistry rules more. And up to this point right here, you already have about 90% of the mass of the solar system. Okay? The rest of the 10% mass is down here in this entire rest of the part of the periodic table. So the majority of chemistry that you would actually encounter in everyday life is actually right here. Okay? These first two periods, that's it. This right here is actually the majority of the mass of the solar system, hydrogen and helium. In fact, hydrogen alone is the majority. So, because of the sun. If you get rid of the sun, then things change. Okay. All right, so B designates the transition elements. These are the ones that go between right here. Most people are going to tell you that they're the transition from one side of the main group to the other. That's actually not true. It's that their chemistry transitions from metal to non-metal. And so you get some unique chemistry right here that's different than these ones over here. And distinct from these as well. Okay? And so they are the transition elements transitioning their behaviors. Okay? Okay, the system can use numbers 1 through 18 for the columns. That's actually the recommended standard by the International Union of Pure and Applied Chemistry, IUPAC. My advisor would add a damn to that. But we should not, because they are actually quite good scientists. They're just, some of their opinions are a little weird. And sometimes they cause things to be a little harder than they have to be, but whatever. You will notice that there are all sorts of periodic tables that you would see that do not follow that standard. And they'll have, for example, 1, 2, 3, 4, like that, A's. And then they'll have B's down here. And then sometimes they'll put Roman numerals here, and this will be 13 for all three of those. And there's actually 3 to 5 different standards, 3 that are mainly used, and then 2 more that are pretty rare. Okay? But different parts of the world actually came up with different standards at the same time-ish. And then IUPAC kind of one-ish. Okay? And so they're sort of the standard, but not fully embraced everywhere. Right? Keep in mind that chemistry, loosely spoken, has about 6,000-year history. Okay? Documented history, in fact, because of China. So, it's pretty incredible. Now, a horizontal row is known as a period. Periods are going to be numbered from 1 to 7. They're going to have sections that with periods 6 and 7. These are actually set apart at the bottom of the periodic table. You notice that these don't have separate numbers down here because they, again, insert right here, right? So they're actually 6 and 7. Okay? We have not yet, as far as I know, gone to period 8. but we're getting real close. So as far as I know, they have not yet made a period 8 element. But that would again be artificial. We have never seen evidence of a period 8 element not artificially made. Okay? Okay. The staircase-shaped line, this is going to be again at boron, and it's going to separate the metals from the non-metals. That's that staircase that I was pointing to before, where I was talking about metalloids. Okay? And so everything to the left of this staircase, here, everybody see the zigzag staircase? Okay. Now, I will point out again that if you look up a periodic table online, you could get one without the staircase. Okay? There are all sorts of periodic tables. I highly recommend, if you look one up, you get the NIST one or the IUPAC one. They're both very good periodic tables and done by people that actually know what they're talking about. Okay? If you get it from some random place, I can't promise you anything. It can be very strange. Okay? Okay, so the staircase right here is going to separate non-metals here, metals here. Okay? Does everybody notice that the metals are in the left and bottom, right? Okay. And see how it actually transitions? If you go here, this is metals, isn't it? Okay. This right here is the stuff that's not really a metal or a non-metal. Every now and then, one of these gets transitioned into being a metal or non-metal, typically up here, because they have more clear properties. Okay? But for the most part, anything that has two sides touching this staircase is what's considered a metalloid. Not really metal, not really non-metal. Okay? The ones that are always getting changed over and modified and fought over are typically boron and aluminum. Aluminum tends to be in the metal category just because it gets used a lot as a metal. And so it tends to be sort of the most metalish. Okay? But it still has some non-metal properties. It just, sometimes they move the line a little to make it a metal. Silicon also gets fought over a fair amount. Okay? And that's actually one of the reasons, by the way, silicon is a semiconductor and is used to make computers and all that. Right? Is its location here. But everything carbon, phosphorus, selenium, these are all non-metals very clearly. And these ones over here are all metals. Okay? Is everybody okay with that? All right. Okay. So all of you probably have some ideas of what are metals and what are non-metals to some degree. Several of these elements, though, there's some important factors we need to talk about in the periodic table. For example, there are what are called the essential elements, or the elements that are essential for human health. Okay? And these are the ones that are typically the largest quantity that's needed for human health is carbon, hydrogen. Hey, thank you so much.
Before I talk about this one thing real quick,
Yeah, sure.
Distract you again. So let's try.
Let me stop recording real quick.
Stop there. Yeah, I'm sorry.
It's okay.